according to the code, a high-rise building is any building having floors used for human occupancy more than 75 feet above the lowest level of fire department vehicle access. So that's just our basic definition for what we're considering a high-rise building. The differences between a residential building and a high-rise is that they're likely going to be cooling dominated even though you're in a heating climate. So cooling and ways to reduce the cooling load become very, very important as opposed to ways to reduce the heating load. The things that affect the cooling load are the density of apartments and the number of appliances per square foot. Right, a residential application, you have one refrigerator, one dishwasher, one dryer. A multifamily building, you could have 300 of those in a much higher density. There's also notoriously a lack of external shading on these buildings. How many high-rise buildings do you see with overhangs, right? So that's not very common. Additional loads such as fitness centers, elevators, recirculation pumps and systems, all of these things increase the internal gains, the equipment in these spaces, and will increase the cooling load. Another difference is that, so because it's cooling load dominated, there's a less emphasis on the envelope as far as efficiency goes. Cooling load dominated buildings, you want to reduce solar gain, you want to reduce internal gains. In a heating load dominated building, you want to reduce heat loss, right? So that's where your envelope focus is. That's where you increase your insulation levels. And I'm going to show you a couple of examples of packages, the differences between packages. So you really can reduce, compared to a single family home, you can reduce the level of insulation that you probably have seen Passive House recommend, right? Like R38 for your walls and, R30 or something or higher for your slabs and things like that. Not necessary as you get into a taller, bigger building. And then what's really interesting is because slabs have that potential to absorb heat, they actually come in handy when you have a lot of internal gains in the building to absorb some of that temperature. So the less slab insulation actually helps on the cooling side. And because the slab becomes such a small part of the overall envelope, it doesn't hurt as much on the heating side. So it's kind of an interesting balance when you're looking at these insulation levels. Solar gains, as I said, very, very big part of the equation for high-rise buildings. Shading is very difficult and costly to incorporate on a high-rise building. You've got to deal with things like birds and, all that kind of stuff. How do you clean them off? Snow buildup and things like that. So how do you shade your windows? Then the solar heat gain coefficient of your glass also becomes very important. There's a balance here. Passive House typically says, if you've looked at any of their literature, they're looking for somewhere around a 0.5 center of glass solar heat gain coefficient. Well, that's too high for these types of buildings. You're going to probably find a nice balance point somewhere between 0.25 and 0.3, depending on the orientation of your building, depending on, some other factors. But for most of the multifamily buildings that I've been evaluating lately, I've done quite a few in the last couple months, the solar heat gain coefficient goes no higher than 0.3 on these buildings to try and manage some of that heat gain. The other thing I wanted to point out here was this is from one of my high-rise projects. You can see the solar gains versus the internal heat gains that are being assumed. They trump, right? The internal heat gains trump because of all of those equipment and all of those people per square foot. So there's only so much you can do about those internal heat gains. You have to have your people. You have to count for your refrigerators. But so where your opportunity is really efficient lighting, really efficient mechanical equipment. And then so that you reduce motors, motor power and things like that, that's going to put heat into the space. And then really focusing on your solar gain to try and reduce that. So as we said, so this is just sort of a visual of, this is a typical floor plan of a high-rise multifamily building, really dense units, 400 square foot. As the internal gains dominate, the solar gains. So this drives up that. So I don't know if everyone knows, Passive House has 3 levels of energy. They have 3 budgets that you cannot exceed. They have energy budgets. So it's a very versatile system. It's a very versatile certification program in that they're not going to tell you have to have this R value here. You have to have this efficiency equipment. They set thresholds for you. It's an energy use per square foot per year, and you can't go over that budget. Okay, so you basically think about your shopping for energy, right? So the primary energy demand is your whole building energy use. And it also includes the efficiency of where your power is coming from. So if it's an electric building, electricity is only 33% efficient from the power plant, right? So if we take your whole building energy use, if it's an all-electric building, we then multiply that by 3. As opposed to natural gas, the multiplier is only about 1.5, 1.05, something like that. So you can see if you have an all-electric building, that primary energy demand kind of goes up pretty quickly. So what happens when you have a really high internal gains is that primary energy demand kind of spikes up. Your cooling energy demand spikes up, but that also drives your heating demand down. So like I was saying, this is just a balance of these 3 values. So high-rise versus single-family. I took a 200,000 square foot high-rise 26-story building, multifamily building, and a 1,600 square foot home. And I put the same exact insulation levels in both, and the same exact heating and ventilation system efficiencies. Everything's exactly the same. And you can see with the insulation package that I put in that meets it for the high-rise project, this is the budget that I was talking about on the right here. This is the threshold that you cannot exceed. Let me point to it on here. This is the threshold right here, the passive house threshold. The single-family home does not meet the threshold for the primary energy demand or the space heating demand. And it's the same exact efficiency levels. So contrary to what would seem logical, the smaller the building, the harder it is, right? That doesn't seem right, but that is how most of these energy programs work, actually. The smaller the building, the harder it is. It has to do with an envelope to volume ratio as well. The air leakage is an issue. So yeah, it's kind of an interesting thing. So what I'm trying to get across here is that you may think, oh God, how am I going to get R38 walls on a 26-story building? Well, you don't have to get R38 walls on a 26-story building. Maybe you're somewhere between R20 and R30, which you can do all day long, right? That's not extraordinary levels of insulation. There's other things that cause more trouble.